here we have a function, we want its derivative. And notice first, we have four things added together. We can do it piece by piece. On the first one, we have the 3 in front and an x to the 7th. Use the power rule on x to the 7th. That gives you 7x to the 6th. 3 times 7 is 21. So we have 21x to the 6th for the first piece. Now, the second one, there were a couple examples like this on the worksheet, but we didn't go over one yesterday. We have square root of x here. And for the square root of x, we recall that we can write that as x to some number. In particular, the square root of x is x to the 1/2. And when it's written as x to the 1/2, it's now written as x to some number, just like the first one. And then we can apply the power rule. So the power rule here with the exponent half gives you a half x to the what? Well, you take the exponent, you subtract 1, 1/2 minus 1, minus 2 halves, so negative 1/2. Any questions about that x to the square root of x part? This one. The next piece we have is sine of x. The derivative of sine of x, positive sine of x, is positive cosine of x from the first of the trig rules. And then last we have a negative, so we can carry that negative down. And e to the x, the derivative of e to the x is itself. So any questions about that one? Maybe I should have made the first number a little smaller for what we're about to do. So here we took the derivative. We started with a function and we took its derivative and we found a new function. We could go on from here, meaning we could take the derivative of this next function, the derivative of the derivative. And that's what we'll start with today. Well, that's the new material we'll start with today. So let's just note, we can then take, this wouldn't answer this example. That example just said find first derivative. But I'll say we can then take another derivative. This first derivative we took, we will call the first derivative. The next derivative, so the derivative of the derivative, is the second derivative. Second derivative, and so on. You can take a third derivative, the fourth, and so on. We will see a couple applications where we use the second derivative. So let's take the second derivative for that. Now, there are a few different notations for the derivative. There are a few different notations for the second derivative. We will see pretty much for the second derivative only one notation. So I'll illustrate the second derivative here. F prime prime, so you put a second prime up here. You could read it F prime prime, F double prime, second derivative of F. But to find F prime prime, we need to take the derivative here. So I probably should have used a different number there, but for this example, I will leave it. The derivative of this function, well, again, we do it piece by piece. First, we have 21 x to the 6th. The power rule on x to the 6th gives 6x to the 5th. 21 times 6 is what, 126? The exponent goes down by 1. You won't have 21 times 6 or anything like that in any of your examples. But then we keep going. Next, we have a 1/2. This one I'm gonna do in 2 steps, actually. First, the 1/2 in front carries along, and then you have x to the negative 1/2, another x to a number. The power rule applies to negative exponents as well. And what does the power rule say? Well, for x to the negative 1/2, the derivative is negative 1/2 x to the negative 1/2 minus 1. It's still number, or it's exponent x to the exponent minus 1. Well, negative 1/2 minus 1, negative 1/2 without 2 halves, so it gives you negative 3 halves. So here, we first have this 1/2, and then we have the power rule after that. Any questions about the second piece there? Okay. Next, we have cosine. The derivative of cosine from the second trig rule is negative sine of x. Derivative of cosine of x is negative sine of x. And then last, again, we have negative e to the x. Negative carries, the derivative of e to the x is e to the x. And if you like your answer like this, that's perfectly fine. I personally don't like having that 1/2 times 1/2, so I'm just going to combine the halves. 1/2 times 1/2, a 1/4, and there's negative x. That's negative 3 halves, negative sine x. Any questions about that? Okay. Before talking about derivatives as a rate of change, which is a small topic before our next larger topic, I'm just gonna right here introduce the notations we use for the derivative. So we've used f prime of x. That's one notation for the derivative. Let's say for y equals f of x, is that how I wrote it here? Say for y equals f of x. So sometimes a function is described as the set of y values given x value. Sometimes it's described specifically as the function. But we have a few notations for the derivative. So the following mean the derivative. Well, the following are used for the derivative. Lousy sentence at the end, but that's okay. First, we have f prime of x, the one we've used. We could also use y prime. So just y with the same prime. We could, and we will use this next one later today, we could use this fractional notation, dy over dx. Now, it looks like a fraction. The derivative is not a fraction. In some ways, there are instances where thinking of the derivative's behavior as a fraction is useful. But it's not a fraction. And one of the results we'll cover in, I don't know, a half hour, will look like we're just working with fractions, but it's not a fraction. Now, one of the reasons a fractional notation is useful is because this kind of looks like a slope, some y over some x. And in the limit, the reason that this notation exists is because of, we can think of the derivative as a slope as an x change goes to 0. But do know that while we will use a fractional notation, the derivative does not, well, the derivative is not a fraction. If you take calc through, I'll mention that. So we have 3 notations for the derivative. We'll use these 3. I'll probably use pretty much only the first and the third, but there are 2 other notations. Now this derivative is, and to be completely technical, an operator, and it operates on functions. Like in that example, we were working on a function. And this notation mathematically describes that, d by dx applied to a function. We'll see this a couple times. And this same thing could be used with y instead. But we will pretty much use the first and the third. Now, one of the other reasons the third notation is useful is because it's frequently, in all of the examples we've seen, we've been applying our derivative rules to x's, and we've been taking limits when we did the definition with functions of x. And keeping that variable in mind is useful for some of the things we're doing, because we're technically taking the derivative using that variable, and we say derivative with respect to x in that case. But we will use these notations, and they all mean the same thing. Now, it may sound strange that we are going to use different notations, but there are some applications where some notations are more convenient than others, especially with the chain rule, which we'll see. Well, I should write it like this. So we've been looking at just general functions. Let's look at, well, we've been looking at functions in general. Let's look at a specific class of functions. So here, our function is going to measure position, meaning the y value would be position, and our x value is going to be time. So this right here is our first application of the derivative. So our function measures position at certain times. We'll pretty much assume time is larger than or equal to 0. But in this situation, where do I want to put it? Let's put it here. So x value is time, y value is position. In this situation, what does the derivative measure? So the original function measures position, where an object is. What does the derivative measure? Well, let's look at this. How should I draw? Let's draw it like this. So here, let's just say our curve looks like this, measuring position with respect to time. Let's look at a way we can see the derivative. So let's take 2 points on that curve and let's approach the tangent line using that secant line, but let's look at the slope a little differently. Let's look at the slope of the secant line just as a change in time and a change in position, meaning we're going to be able to form, using the secant line, the right triangle. So the x value is a change in time. Y value is a change in position. So what would the slope of the tangent line at that first point? I don't want to introduce another letter, but I guess I have to. Let's call this T. Let's call it A. I don't want to have T's all over the place. So using that setup, what is the slope of the tangent line at A? Well, we have a secant line, we can use that to approach a tangent line. So there, the slope of the tangent line at A is that right here. Is what? Well, it's the limit as our horizontal value goes to 0 via delta of time. So limit as the x value goes to 0 of the slope of the secant line. But in particular, what we are taking the limit of is a change in position divided by a change in time. A change in position divided by a change in time measures the velocity. By the definition we're about to do, but in general, in physics, the change in position, how an object's position changes as time changes, measures the velocity. So let's just formally define this a little. Where should I write it? I kind of want that graph to stay on the board. So definition. When over here. Okay, that's much better. Let. We in the previous discussion had a function which measures position with respect to time. Let's call that S of t. Let S of t give the position of an object at time, well, maybe it's 4 times t. So S of t gives the position. Well, from that discussion, the first derivative is going to measure the velocity. So I'll just say S prime of t is the velocity function. S prime of t is going to measure a change in position given a change in time at each point on the curve. So S of t gives the velocity at any t value. And sometimes we'll use S prime, sometimes we'll use V of t. So maybe I should have said that. Sometimes we'll talk about velocity function as V of t instead of S prime of t. Well, they are the same function. To find the velocity function, we take the derivative of a position function. And we can go on from there. We can take the next derivative. I won't describe this one in detail like we did the first one, But the second derivative of position with respect to time, the derivative of velocity, is the acceleration function. It measures how the velocity is changing for any time. This is the acceleration function. Now, velocity measures a change in position divided by a change in time. And implicit in that is an understanding of how position is changing. Meaning, if you start at a given point and you walk forward, your change in position is going to be positive. If you start at a given point and walk backwards, your change in position is going to be negative. And there are times where, we'll see a couple applications of these later in the semester. Actually, our last application for week 6 will be an application of interpreting derivatives as a rate of change. But always in the back of your mind, and we will see this, recall that velocity implicitly has a direction understood, meaning a forward direction versus a backward direction, so that you can measure a position. But sometimes it's nice to not take that direction into account. If you're walking forward at 50 miles per hour versus walking backwards at 50 miles per hour, it may be useful, and it will be useful a couple of times, to treat them the same for interpretation. And we call that the speed. So I'll just say absolute value of our velocity function. The absolute value is going to treat walking forward and walking backwards the same, because the negatives become positive. So the absolute value of the velocity, making those negatives positive. Also we can find that the absolute value of first derivative is the speed function. And the speed function is going to treat walking forward and walking backwards the same. And there's one more function we'll see a couple times. So let's call this part D. The average velocity. The average velocity, well, average on what? On a time interval. On time interval. Let's close the interval, let's call it A to B, is what? V average is the average velocity on a time interval. Well, this is actually identical to the slope of a secant line for those 2 points. Slope of the secant line is given by a change in y divided by a change in x. The average velocity, a change in position, divided by a change in time. So we have these 4 definitions. Let's just do for now to introduce these and to illustrate a couple of them. Let's do this example. Let's do 2 examples. Yes, let's do 2 examples. But I have to erase that. Any questions about these definitions? Perhaps the examples will make it a little more clear. So in one of the videos this week, we covered the mean value theorem. And mean value theorem, very important. But there is a nice interpretation of the mean value theorem when the function measures position. And one of the worksheet problems discusses that. The one with average velocity, because this looks like the left-hand side of the mean value theorem versus instantaneous velocity, meaning velocity at a point. Which example should we do? This one. A particle moves along an axis. Well, let's just say moves so that we're only using functions of one variable, so it's moving on an axis, so that its position at time t is given by this function. Where did I write it? T cubed minus 9t squared plus 24t plus 4t greater than or equal to 0. Time is going to be only positive or equal to 0. So we have a position function. When is the particle at rest? That's our question here. When is the particle at rest? Well, when a particle is at rest, what's happening? Well, it's not moving. It's not changing its position. When is a particle at rest? When its position is not changing. How can we figure out when the position is not changing? Well, which function deals with a change in a position? The velocity function. Now, average velocity is written over here, and it looks like this is a change in position, and it is, but there's no time interval that we're looking at. We're looking at all times, when is the position not changing? It's not changing when the velocity is 0. Let's say set velocity equal to 0 for this. Well, we need a velocity function. Velocity is the derivative of our position function. So we're going to take its derivative, a few power rules here. Our variable is t, and in math we say we're going to take the derivative with respect to t, meaning all those rules with t's instead of x's. But here we have some power rules. So the first one, t cubed, derivative would be 3t squared. The next one, we have t squared, derivative is 2t times a negative 9, so negative 18t. This one, remember with the power rule, we can show that the derivative of a constant times a single variable to the first is just that constant. And then 4 is a constant, derivative of that is 0. So we want here to set this derivative equal to 0. So let's do that. Set it equal to 0. I'm not going to set it equal yet. I'm going to factor it first. How can we factor this? Well, if 3t squared, conveniently here, the 3 factors out because everything is a multiple of 3. T squared, negative 6t, positive 8. And that inside does factor as well. Because what? 4 and 2 make 8. 4 and 2 make 6. They're both negative. So t minus 2, t minus 4. We want to set that equal to 0. I guess I'll finish this over here. And that equals 0 when 3 equals 0, which is never. When t minus 2 equals 0, t minus 2 is 0. When t equals 2, that's not 21. That's a bad vertical line. And t minus 4 is 0. And t equals 4. So here we have 2 times at which the particle is not moving. Any questions about that one? Okay, let's do one more example. Do I want to do that one or do I want to do this one? Which one's better? let's do this other one, the numbers will work out a little better. I'm gonna erase this to be a longer example. Example. If a rock is dropped from a height of 100 feet, then its position above ground t seconds later is given by this position function. You're not going to have to know how to derive a position function. You'll be given position functions. This is a math class, not a physics class. So if a rock is dropped from a height of 100 feet, then its position above ground t seconds later is given by that function. And we're going to have 4 parts. Actually, we're going to have 3 parts. Combining 2 examples. They have 4 total questions. Yeah, let's do it like that. So 4 parts. When does the rock hit the ground? Part A. At what time does the rock hit the ground? Find part B. Find the velocity at this time. At this time, meaning the time found in part A. Now find the velocity at this time. The velocity is a function. The velocity takes time as its input. The velocity can take any time. But when we talk about velocity at a specific time, sometimes we call that the instantaneous velocity. And the derivative gives the velocity at that discussion with the graph we had actually is finding the instantaneous velocity at A. INSTANTANEOUS velocity. So there we're looking to find the velocity at that time, find the instantaneous velocity. Now I tend to use that word very frequently because of how long it is and how many syllables it has. Part C, find the average velocity during this fall. Meaning the rock is being dropped. It starts at a time 0, it ends at the time that it hits the ground. We're going to find the average velocity during that time interval, but we have to figure out the time interval. So for now, we'll just say during the fall. And part D, at what time does the instantaneous velocity, so this will probably be the last time I write this exact word. At what time does the instantaneous velocity equal the value found in C? We have 4 parts here. When does the rock hit the ground? Find the velocity at, maybe it should say at the time found in A to parallel part D. Find the average velocity during that time interval, and at what time does the instantaneous velocity equal the value found in part C? At what time does the instantaneous velocity equal the average velocity? So let's start with part A, because we need that for part B and we need that for part C. When does the rock hit the ground? Well, for this, what does our position function measure? The position function measures the position above ground. So what is the position when the rock hits the ground? Well, when the rock hits the ground, it's 0 feet above ground, because our position function measures height above ground. So it'll hit the ground when it's 0 feet above ground. So here, what we need to do is set our position function equal to 0. And what do we get? Well, negative 16t squared plus 100 equals 0. Now it'll be assumed in these only positive times matter. I don't think I've ever actually taken off if people use the negative times, because they usually don't make too much of a big deal about negative times. Well, we'll see in a moment why. Solve this for t. Well, we can add 16t squared to both sides. So we get 16t squared equals 100. We can divide by 16. So we get t squared equals 100 over 16, 50 over 8, 25 over 4. Solve this for t. We get t equals 5/2. And we're not taking the negative because we won't have negative times here. T equals 5/2, so 2.5 seconds. Any questions about part A? Okay, so we found the time at which the rock hits the ground. So part B says, find the velocity at this time. Well, part B just says find the velocity at 5 seconds. So we need a velocity function. We need to evaluate it at 5 seconds. What is our velocity function? Now, and don't be worried about fractions. Fractions are here to help you. Fractions are very convenient mathematically. Far, far more convenient than decimals. Especially for a problem like this one. We need a velocity function. Well, we have t squared. Derivative of t squared is 2t to the first by the power rule. And this negative 16 carries along. We have negative 32t. 100 is a constant. Its derivative is 0. Any questions about finding the velocity function? So what we need to do here is evaluate it at 5/2. Negative 32 times 5/2. Well, you could do 32 times 5 and then divide by 2. I will do 32 divided by 2 is 16. 16 times 5 is 160 divided by 2, which is 80. And there's a negative. Maybe I should throw units on these. And just like with not worrying about negative times too much, I really don't care much about units. I mean, that these work no matter which units we throw on these. So. But there will be maybe 1 or 2 things where keeping track of the units does help us. So I'll include units here. Velocity is in, I erased it, I think it's feet, and the other one is seconds. Negative 80 feet per second. Notice here we have a negative velocity, because if you drop a ball, its positive direction with our function is assumed to be up. Or we're using a rock, right? I think we're using a rock. If you drop a rock and get that function for your position, the positive direction is upward, negative direction is downward. That's reflected in or with this negative velocity. Any questions about part B? Let's put a rectangle around that because we did that for part A. So another way of saying that is the instantaneous velocity at 5 seconds is -8 feet per second. So at that instant, it's -8 feet per second. Find the average velocity during the fall. Well, the fall starts when the rock is dropped at time 0. It ends at 5/2 seconds. So here we want the average velocity on time interval 0 to 5/2. Okay. So we need here, remember the average velocity is given by the change in position on that interval divided by change in time on that interval. Change in position is what? Oh, I still have a position function here somewhere. So the work we did in part A actually tells us that S at 5/2 is 0. So we, for this one, actually don't have to do any algebra for that first one. Minus S at 0, what happens when t equals 0? You get 0 plus 100. So minus 100 divided by 5/2 minus 0. 5/2. Now we need to simplify this. We get what? -100 divided by 5/2. And I always like exaggerating a fraction bar when I have layers of fractions. -100 is 2/5. 100 divided into 5 is 20. 20 times 2 is 40. There's a negative, so -40. And our units here are also feet per second. Any questions about part C? So we have here an average velocity. The mean value theorem tells us and if you watched the mean value theorem video, then you've seen this. If you haven't, well, this is what you need to know. The average velocity is directly a change in y divided by a change in x, meaning it's the slope of a secant line. Well, it's the slope of a line, and in this case, it's the slope of a secant line. The mean value theorem in general says when you have this situation, you can find a point in between them where the slope of the tangent line equals the slope of that secant line. And we can interpret the slopes of both of those lines. You know, without even thinking of position, the slope of this lower line is the change in y over the change in x. The slope of this tangent line is given by the derivative. And since those lines are parallel, those two quantities are the same. The mean value theorem video goes into a little more detail with that. But the interpretation when the function measures position looks, when the function measures position, that result still holds. And the interpretation is that the lower line gives the average velocity, the upper line gives the derivative of our position function, the instantaneous velocity at that point. And part D is really asking at what time is the mean value theorem verified on that time interval. And we are going to see in part D that this value does occur between 0 and 5 halves. So at what time does the instantaneous velocity equal -40? Well, we need to set our velocity function equal to -40. If you haven't viewed the mean value theorem video, it's a good idea after that to just look back at this example, part D. If you have viewed it, it may be a good idea to spend a little bit of time just thinking about how part D is really asking a mean value theorem question. So here we want the instantaneous velocity to equal -40. Well, instantaneous velocity, a general velocity function, is -32t. Set that equal to 40, divide by -32. 40 into 32. 8's cancel, and you're left with 5/4, and this is seconds. Units, so it's units. Any questions about this one? Any of the 4 parts? Notice that 5/4 is between 0 and 5 halves, as that curve over there suggests it should be. Next, we're going to talk about chain rule. What is the chain rule? Well, let's start over here with an observation. Chain rule is a theorem. It's a very important theorem in calculus. The chain rule is going to lead to some structure for certain derivatives. And those of you who are going to take Calc 2, the first thing you do in Calc 2, which is not a part of Calc 1, really drives into you the importance of viewing the chain rule as a piece and another piece. So let's see what I mean by that. Let's first observe, not recall. Observe. We can find a derivative of this function. F of x equals sine of x. Using our derivative rules, we can find, for example, the derivative of sine of x. It's cosine of x, using the derivative rules. For the chain rule, it's very important to have some practice using the derivative rules. We can find that derivative. We can't yet. Can't, however, find the derivative of this function. Sine of 3x. Now you might think that you could use one of those trig identities or something to simplify it, but it would still not turn into functions on which the derivative rules apply directly. So we can use derivative rules to find the derivative of the first one. We can't for the second one. Why? Well, notice in all of those derivative rules, our variable in consideration is just an x. Meaning up here, our variable is just that single x. Down here, it's x with something else. Now there's a 3 in front of it. When that 3 is there, and then notice in the derivative rules, there's nothing about how to take the derivative of sine of a number times x. And for the chain rule, it's very important to see when your variable is just an x versus a 3x. The chain rule tells us how we can extend these derivative rules to taking derivatives of a function like that. So let's state the chain rule. And then for the next half hour, maybe we'll do some examples using the chain rule. I will introduce two notations for the chain rule using our derivative notations. Technically, this first function and the second function are compositions of functions, but the first one is a trivial one, meaning just an x. This is sine of 3x. You break it into a composition, sine of x evaluated at 3x. And the chain rule in general tells you how to take derivatives of a composition of functions. So here we have the notation derivative with respect to x of a composition. And the chain rule tells us how we can take that derivative. We can do that. A composition has an f and a g. The g is inside the function f. And it's very, whenever I think of chain rule, I don't think directly in terms of compositions. You know, because actually breaking this down into a composition with an f and a g is, you know, that's seems like having to go through way more thought than is necessary for something that's going to show up throughout the semester. Because of that, I like thinking of a composition purely in terms of a first and a second function, an outside function, sine of x, and an inside function, 3x. The derivative of a composition is given by the derivative of the outside, where we leave the inside alone, and then we multiply by derivative of the inside. So here, the chain rule has two parts. Derivative of f times derivative of g. Now, that equation has a lot of notation. It uses both of our derivative notations. It has two functions. It has large parentheses, medium parentheses, small parentheses. So that may not be the most useful form that the chain rule can take. And I believe it is not. This uses two of the derivative notations. The fractional derivative notation makes it much more clear what's going on with the chain rule. We want to find the derivative of function y with respect to x, which we will. dy dx is the derivative. But the chain rule says we can introduce another variable to deal with this 3x. We can call it u, letter u. And it's still going to have these two parts that are multiplied together, as we have up here. And those two parts are actually the same. You know, the first part here is the same as this first part. And the second part is the second part. But this notation, the fractional derivative notation, one of its conveniences is that it makes the chain rule look a little nicer. Now, this equation on the right-hand side makes it look like these are exactly fractions. Meaning it looks like these du's, du divided by du would be 1, dy dx equals dy dx. Now, these are not fractions. But for our purposes, you can think of them like this. If you go on to take Calc 3, in Calc 3, you'll have functions of more than just x, functions of multiple variables. And its corresponding chain rule, it has a bunch of these added together. And the fractional notation does not apply, or it does not hold exactly. But for our purposes, you can, in order to understand chain rule, in the back of your mind, think these look like fractions. And you can use that fractional simplification to help keep yourself organized when you do these examples. So right now, we can take the derivative of a composition of functions. What does that look like? Well, let's see, it's 2 o'clock. That last result will probably take up to a half hour. Let's do maybe 6 or 7 examples illustrating this. Let's start with this one. So before, we've been doing find f prime of x, and I've been saying f of x is whatever here, because that second notation is much nicer. I'm just going to say y in terms of x. Example. Find dy dx. Y equals sine of 3x. So you can translate this into the first notation if you want. The first notation is useful for theoretically examining the chain rule. It's not really, I can't imagine anybody actually finding it useful for directly notating the chain rule. Those two notations were actually, there's a reason both of them exist. Calculus was discovered by 2 separate people at pretty much the same time, and there's no reason to believe either of them knew that the other was doing it. One was Isaac Newton, and he preferred this notation. He used that notation. One was Gottfried Leibniz, and he used this notation. And his reasoning for using this notation, well, it follows from that velocity discussion where we look at that the limit of the change in y or the change in x. But he also observed that there are times where it does behave like a fraction, and there are times where it doesn't. So viewing it like that can help you understand the derivative. But they were both discovered at the same time. They both are useful. They both are illustrative. So we still use both. But for these examples, I will use the second notation. Find dy dx, y equals sine of 3x. Well, our goal here is going to be to introduce a variable u so that we can find both of these derivatives using the algebraic, or using the derivative rules. Sometimes I call them algebraic derivative rules, but they're not all algebraic. Just the first 6 are. So our goal, find a u which allows us to take 2 derivatives which we can multiply. Well, in finding the u is, well, the hardest part if you've practiced the derivative rules. But with practice, it does become more natural what is going to be our u value. Here, we know how to take the derivative of sine of just x, sine of a single variable. So we will let u be this 3x so that y is just sine of u. That's a u. So y is just sine of u. Now we can take dy du, we can take du dx using our derivative laws. So what is dy du? I'll say Yeah, so is a good word. So dy du, the derivative of y with respect to u. Y is sine of u. Now just go through the derivative rules, replace the u with, or replace the x with u. Derivative of sine is cosine. So the derivative of sine of u is cosine of u. And du dx, first line, y is now a function of u. Second line, u is a function of x. Du dx, using the power rule, is 3. We're using that constant observation is 3. Any questions about what we did so far? Okay. And now we can find dy dx by multiplying those. It's dy du times du dx. Dy du, cosine of u. Du dx is 3. And in our final answer, if we can get rid of u, we should. Meaning if we can replace all the u's with x, we should. In this case, u equals 3x times 3. I'm just going to put the 3 up front so it looks better. So we needed to find a u and then apply yesterday's derivative rules. Any questions about that one? Now, with practice, you can make some convenient shortcut observations. This weekend, it's definitely a good idea to practice doing some of these. You know, there are some homework problems on them, but you know, even beyond that, it's a good idea to continue practicing problems like these. One observation you can make is the following. Where do I want to make it? Let's make it here. Let's erase this. Let's, for now, erase all references to u. Letter u. And let's just write the answer over here. We have our function, we have its derivative. For pretty much all the examples we cover here now, I will go through the u substitution because you know this is an observation you make after practice, but I will make it now. I'll probably mention something about it in each example. Without going through u, how can we find this derivative? Well, maybe I'll use a different color because there are 2 parts. Let's see, here's blue, here's red. We have here y is a sine function. Y is the sine of something. It's a sine function. A sine function by the derivative rules has derivative a cosine function. The derivative of a sine function is a cosine function. So the algebraic derivative rules, the derivative laws, don't apply when that something is anything other than a single variable. But if it is something other than a single variable, as it is here, you know, there's that 3 there, we can still think of those rules as directly applying by taking the derivative of sine, which is cosine, and leaving the 3x alone. But then the chain rule says that what we have to do is multiply by the derivative of this 3x. So another way of viewing the chain rule is by taking the derivative as you normally would, meaning derivative of sine is cosine. But then the chain rule says, remember to multiply by the derivative of that piece there. And the u substitution really does show that in detail. Any questions on that observation? But for these, I will go through the u substitution because this is really something you get used to with a good deal of practice, and you know, one problem usually isn't enough practice. So let's do this one. Sine of x squared minus 3x. So now we still have a sine function, but its inside is far more than just an x. So what we can do is use a u substitution. Use x squared minus 3x. Y is now a function of just u. And with this substitution, we can find dy du. We can find du dx. dy du, y is sine of u, the derivative of sine is cosine of u. U is x squared minus 3x. The derivative there, power rule is 2x minus 3. Power rule or the constant observation. So dy du, cosine u, du dx, 2x minus 3. So dy dx is these two multiplied with that substituted back in for u. Then dy dx is those two multiplied. I'm not going to write dy du dx for this one, but it's cosine of u times 2x minus 3, which is, I'm going to pull the 2x minus 3 out front. I think it looks a little better. Plus it parallels the first one much better. So replace u with x squared minus 3x. Any questions about that second one? And you can observe that the same observation we made over here does apply. Derivative of sine is that cosine piece. Leave the inside alone and then multiply by the derivative of that inside. And with these chain rule problems, you don't have to go through the details. And later in the semester, as the semester goes along, for some of them I will write the details, but for most of them I won't. But for today, directions here are all going to be find dy dx, so I'm not going to keep writing it. Any questions about that second example we just did? Okay, let's do this one. So with sine and cosine, it was pretty clear what our y function was, what our outside function was. And with all trig, really. How about this one? Now let's make it cosine. That's different. Now let's make it, cosine for now. Example. Here we have x to the 5th plus cosine x all raised to the 7th power. we want its derivative. Well, you can expand it out. It would actually require 6 chain rules if you did that. But what we can do is observe that this function is something to the 7th power. And we can make a u substitution, which makes it look exactly like something to the 7th power. If we let u be this entire inside piece, then y is u to the 7th. So if we let u equal x to the 5th plus cosine x, then y is u to the 7th. Notice in all of these examples we've done and all that we will do, once we make our u substitution, we're back into derivatives that we could have taken yesterday. And that's really what chain rule does. It reduces the composition to, it reduces taking the derivative of a composition to applying derivative laws. So what is dy du? Well, it's u to the 7th, so derivative of that with respect to u, power rule 7u to the 6th. And what's du dx? Well, 2 pieces, derivative 1 by 1. Power rule on x to the 5th, 5x to the 4th. Derivative of cosine, remember, is negative sine. The derivative of sine is positive cosine, but the derivative of cosine is negative sine. So dy dx, which I didn't write the directions, all of these are going to be fine dy dx. Then it says dy dx is those two multiplied together. 7u to the 6th times 5x to the 4th minus sine of x. And we just want to get rid of u because we can. 7 times x to the 5th plus cosine x all to the 6th times 5x to the 4th minus sine of x. So when you're looking at any derivative problem where you have to use the chain rule, it's always a good idea when you're done to just take a step back and notice if you have the 2 chain rule pieces. Meaning, now there's the dy du part, the du dx part. Here we have this piece, we have this piece. And notice here that the derivative of that left-hand piece, in parentheses, equals this right-hand piece. So if you didn't want a u substitution here, you could say, well, we have something to the 7th. Derivative of something to the 7th is 7 of them to the 6th. Chain rule says multiplied by that derivative. Any questions about that? Let's do a couple more of these. What's a good one to do? Let's do these 3 examples, and the first 2 will go to the third one. So right here, we're going to do 3 examples that are, the one will be simpler than the next, but the goal here is going to be to build toward the 3rd example. So I'm just going to write something like that. I'll call this a separate example again. The next 2, let's just say build the The next two will build to the third one. Well, what are the next two? Let's start with the next one. This is similar to the first one. Derivative of tangent now of 3x. What is the derivative of tangent? Well, derivative of tangent of x is secant squared. But we don't have just an x, we have 3x. So what we can do is use a u substitution. If we let u equal 3x, then y is now tangent of u. Then dy dx is dy du. Derivative of tangent is secant squared. So there's our dy du times du dx times 3. And I'm just going to rewrite this with the 3 out front. We have 3 secant squared of 3x. So in that one, I didn't directly write out dy du dx, the details. But in that last line, it is implicit which ones are which. Here's our dy du, there's our du dx. Any questions about that one? That's very similar to the first one. Okay, next, let's do this one. Find dy dx here. Tangent of 3x times secant of 5x. Well, before even noticing anything about the chain rule, we have here two functions of x multiplied together. We have tangent of something times secant of something. So right from the beginning, we observe we have a product, meaning the derivative will require use of the product rule. Is this going to fit? I think it will. We need a product rule. What does the product rule say? Well, it says derivative of this times this plus this times derivative of this. 4 antigrams. So first we need the derivative of tangent of 3x, which we found in that example. So we have 3 secant squared of 3x is the derivative of the first. What does the product rule say to do next? Take the second. So there's 1/2 of our product rule. What does the rest say? Well, the rest says add the same thing, but the opposite, meaning add this piece times the derivative of this piece. I'm going to put the tangent of 3, I'm going to put a gap. There. Product rule, derivative of the first times the second plus the first times the derivative of the second. How do we do the derivative of the second? Well, we do it just like we did that first one, except we have a secant and a 5x. What did we do here? Well, we took the derivative of tangent, it gave us the secant squared of 3x. We had a 3x, derivative of that was 3. Here we have a 5, the derivative of 5, or sorry, here we have a 5x, derivative of 5x is 5. So I'm going to put that 5 out front instead of right in the middle. Derivative of secant is secant times tangent. And don't worry about simplifying. this. But do take a step back, and I'll use the colors of chalk to observe the four pieces of the product rule. So here we have the derivative of the first. Here we have the second, plus the first, which is that, times the derivative of the second. And for organizational purposes, I just moved that 5 out front. Any questions about this one? Okay, so I said before, these next two will build to the third one. Well, here are these next two. What's the third one? The third one is this one. So really, the first built to the second, and the second is going to build to the third. Now this one, next one's pretty nice for illustrating the structure of the chain rule. Find dy dx here. So really, I could have asked this one right at the beginning, but especially since this is our first time doing chain rule, it's nicer to build to. Well, yeah, okay. Let's take our tangent of 3x times secant of 5x. But instead of just taking that, let's raise it to the negative 70 third power. That hesitation was thinking about negatives, thinking about the power rule with negatives. To make sure this looks the way I want it to. Find dy dx here. Well, we have a lot of functions here. Well, there's one function, but it can be broken up into multiple functions. But in its most basic sense, it is a function raised to the negative 73rd power. For this one, because of how it built up, I'm not going to write out the u substitution. But for this one, we have a function to the negative 73rd, a function to a number. The derivative of a function to a number uses the power rule. So we have negative 73 raised to the negative 73 minus 1, which is negative 74. What do we raise? Well, we're raising this whole inside piece, this whole tangent of 3x times secant of 5x. We raise that to the negative 74, but the chain rule says we need to multiply by this derivative. So you could have done u equals all of that. Y equals u to the negative 73rd, dy du, negative 73u to the negative 74th. Du dx is the derivative of that. But notice in the previous example, we found the next derivative we need. So I'm just going to say times large capital star, where star is, well, in your notebooks, if you're going top to bottom, point up or something, I'll draw a large arrow over there. Maybe I should have said where star is in the map. But why does this work? Well, if you let u equal this, dy du, negative 73u to the negative 74, du dx is just that derivative we found over there, and with a u instead of a y. And for this one, because of the building up, I will answer it like this. And a problem like this is nice for illustrating the chain rule. Any questions about that one? If you have one where you already did a derivative and you have something in a future problem that references it, you can do that same type of star argument if you want. Any questions about that one? Okay, let's do two more. Yeah, let's do two more. And then we'll move on to our final topic for the week. Let's do this one. Square root of 5x to the fourth plus x. Well, here we have the square root of something. And with the derivative rules, square roots, I'll mention something about them later, either later today or beginning of next week. But the derivative rules apply when the exponent is a number. So we can write this as 5x to the fourth all to the 1/2. And we have something raised to the 1/2, we can let u be that something and then apply the chain rule. So we can let u be 5x to the fourth plus x so that y is u to the 1/2. And now we can find our two pieces of chain rule. Yeah, let's do it over here. Now let's do it over here. dy du, we have u to the 1/2 power rule. We saw that earlier actually in the first example. Half u, negative half, 1/2 minus 1, negative 1/2. du dx is a couple power rules, 20x cubed plus 1. So now, then dy dx is these two multiplied together. Half u to the negative half times 20x cubed plus 1. You could write that as a fraction, 20x cubed plus 1 over 2 root 5x to the fourth. What am I doing? That's wrong. How did I notice that was wrong? Well, it's not because I looked over there. That's actually a good mistake to make right now in Illustrator. How did I notice this was wrong? Well, I noticed that the derivative of this piece right here that is written there is not that piece. Because the derivative of 1 is not 1. Derivative of x is 1. That's actually the first time I've made a mistake like that while teaching it. So that's a very good mistake to make actually, because it shows you how you can check your work by taking a step back. But what was I saying? You could write this as a fraction, 20x cubed plus 1 over 2 root 5x to the fourth plus x. In some applications, it will be, and for future simplification purposes, it will be nice to write this as a single fraction. For now, I would recommend not worrying about that for now. Next week, yeah, I probably should do it next week. Next week, I will mention something about the square root also. Well, any questions about that? Let's do one more. Let's do, how about some nested trig functions, nested trig. Oh, I guess we didn't do an exponential, so we have to do 2 more. Let's do 2 more. Let's do the exponential first, because that's probably easier than the second one. Let's do 5 to the, what trig functions have we? Let's do 5 to the cotangent of x. 5 to the cotangent of x. Well, what is this function? This function is 5 to something. 5 to something. With all of these, I could have said break it into a composition. F of x is 5 to the x, g of x is cotangent x, y is f of g of x. But I like the 5 to something discussion more, because it lets you turn your somethings into the u's that you need. So here, 5 to the cotangent of x, we can use a u substitution. That's not how you spell x. We can let u equal cotangent of x, so that y is 5 to the u. Well, then what do we have? Well, we have half of our work written over here, if I erase properly. We have dy du, we can find dy du, we can find du dx. Du dx, derivative of cotangent is negative cosecant squared of x. Dy du, we have 5 to the u. Use the general exponential rule. The derivative is itself times natural log of the number, the natural log of 5. So now dy dx is those two multiplied together. I'm just going to pull this negative way out in front of everything, just so it looks a little nicer. Now, when I do these things to make them look nicer, it's definitely something worth noting. In your work, I think you're great at work. I'm not going to take off if it doesn't look that nice. Meaning if you wrote the times negative cosecant squared of x, but do make sure you multiply by negative, not subtract. But here, just going to pull the negative way out front. Negative that times cosecant squared. Oh, but we don't want u in our answer. I should have done that, and that's so let's replace u with cotangent of x. So negative 5 cotangent of x times the natural log of 5 times the cosecant squared of x. And with this one, you can see the one-step method of doing the derivatives. Derivative of 5 to something is this piece. 5 to that thing, log 5. And then derivative of that exponent, negative cosecant squared of x. Any questions about that one? Let's do one more. Let's do this one. Find dy dx for, how many negatives do I want? Let's do cosine of tangent of, let's just do x to the 5th minus x to the negative 2. So right here we have, what you could call nested trig functions, cosine of tangent. But if we want the derivative, we can do that using chain rule. And let's look at the details of that. Well, how would we figure out u? Well, it may be tempting to say u is the x to the fifth minus x to the negative 2 part. But if you do that, then y is cosine of tangent of u, and you'd need another u substitution. So that could work. I think that's a little more complicated than the following substitution. And we can arrive at the following substitution by observing that in its most basic sense, y is the cosine of something. Y is the cosine of something, so let's write y as the cosine of something. Let's call it u, because that's the standard letter for u substitutions. And how did we arrive at that? Well, we let u be the tangent x to the fifth minus x to the negative 2. Any questions about that substitution? Now, well, let's find dy du and du dx. Dy du, the derivative of cosine, is negative sine. Du dx, the derivative of tangent. Well, we have there tangent of x to the fifth minus x to the negative 2. So technically, we would need a second u substitution, meaning that piece in there would become another u. We've seen a derivative of a trig function 3 or 4 times today. So I'm going to do this in the one step by observing u is a tangent function. The derivative of a tangent function is a secant squared function. What the chain rule says, multiplied by the derivative of what we would substitute. Derivative of x to the fifth, 5x to the fourth, derivative of x to the negative 2. Well, ignoring this first negative, power will give you negative 2x to the negative 3. The negative and the negative 2 become a positive 2. The exponent goes down by 1. Now dy dx is negative sine of u, which is tangent of x to the fifth minus x to the negative 2 times the derivative here, secant squared of x to the fifth minus x to the negative 2 times I'm going to put a square around this. No, that square is not trying to scale. So this is kind of a long answer, but with the details of the u substitution, the pieces jump out over there. Any questions about that? Now, before moving on to our next topic, let's just compare our original function to this answer. Our original function was a cosine function. The derivative of a cosine is a negative sine. And we have that right here. But the chain rule says multiply by the derivative of that inside piece, which has another inside, which means you need to multiply by the derivative again. So in a sense here, we're working from the outside in, if you want to do this in one step. Negative sine of this times derivative of this, secant squared of this times derivative of that. So in a chain rule, you could have multiple chain rule type steps. Any questions about well, any of the chain rule examples we did? So it's definitely a result which requires some practice to get used to. On the worksheet, where did I put the worksheet? Let's see. I can't find my worksheet, but it was on the second page. There was a question. I think it was find dy dx. Is this the worksheet? That looks like it. On worksheet 3, number 8, several chain rule questions. So the worksheet is, the derivatives on the worksheet are divided into ones without chain rule, ones with chain rule, problems 3, problem 8. But do notice the homework is not divided that way. There's just the one, number 2, which says find some derivatives. Now, those problems A through G are separated into, I'll look at that part, F is cosine of tangent. That was certainly not intentional. Although it probably was the same reasoning because I wanted the one negative to show up. But the problems in A through G are technically divided into ones which require and don't require chain rule. But it's definitely a good idea to practice these over the weekend, even after the homework. Now, any practice you do with chain rule will make the structure of the final answers a little more clear. So, any questions about that? So in calculus, there are a few large theorems we cover. We've discussed the mean value theorem. We've discussed the chain rule. There's another large theorem called the extreme value theorem. And, well, that's what we'll discuss next. Extreme value theorem. Sometimes abbreviated EVTXET. I probably won't abbreviate it at all because I think I'll write it exactly twice. But to get there, we need some language. And to get this language, let's call it a definition. And let's use a graph to motivate the definition. Let's make the graph look like this. Okay, let's mark off some points. Here's 6, here's 4, here's 2, there's 0. Let's say this is at 1. Let's say this is at 3. Let's say 6 goes through 6, 5. Those 2 and 4 are at the top and bottom of those little curves there. But what we're going to do, here's a function. But we're not going to look at the entire function. We're just going to look at the piece from 0 to 6. So consider f of x on the closed interval 0 to 6. We say f of x has, this will be 4 definitions, absolute maximum. First definition. So again, we're looking only from 0 to 6. So we're looking only at that shaded in piece. Maybe in case the shading is not clear, I'll mark it with the beginning and end like that. We're looking only at 0 to 6. Absolute maximum is going to be the largest y value it hits. the largest y value on this interval is 5. So it has absolute maximum 5. And we'll also say when it occurs, it hits 5 when x equals 6. And so I don't write the same sentence a bunch of times, I'll just say like this: f of x has absolute minimum. Absolute minimum, just like absolute maximum, will be the lowest the function gets, the smallest y value the function hits. The smallest y value is over here, y equals 0. The absolute minimum is 0. When does it occur? When x equals 0. We say f of x has local. And those are absolute, sometimes see referred to as global. I like absolute more. We say f of x has local maximum. Now, a little more on local in a moment. But for here, we'll just say a local maximum will occur at a point like this, where it's at the top of some sort of mound. It could be a pointed mound, like an absolute value mound. But when we have that point occurring at the top of a mound, we're going to call that a local maximum. And it'll be the y value, local maximum of 3. And it occurs when x equals 2. And similarly, f of x has a local minimum at the bottom of a mound, which in that case occurs when x equals 4. The local minimum is the y value, local minimum of 1, when x equals 4. We have 4 definitions: absolute maximum, minimum, local maximum, minimum. The locals will occur tops of mounds, bottom of mounds. And the absolute will be the largest value. Now, well, any questions about those definitions? So local is also sometimes called a relative maximum, relative minimum. Local in math, I prefer local because local in math does have a technical definition. Local in math means, now let's look at the maximum. It's a local maximum because, those are parentheses, because if you look really close to 2, so if you look at what happens at 2 and nearby, it's the largest value. And local just means you're looking nearby the point. I'm not going to ask you that, but it is, there's a reason. And when I took calculus, I preferred relative maximum, relative minimum. But when I learned the word local actually means something in math, I started using local. So you can use whichever one you want, local or relative. But let's make one observation about these definitions. Observe in this function, right here, let's mark off that top point. Let's call it 5. Let's call it 2. Observe, let's say, observe that on, let's say, we could use the entire real number line. Let's just say observe that in this function, the local maximum is still the top of this mound. But what if I asked about an absolute maximum? Well, the absolute maximum is still the largest value it hits. The largest value the function hits is 5. So in this case, the local maximum is also an absolute maximum. Observe, this local maximum of 5 when x equals 2 is also absolute because it is the largest value the function hits. We'll also just make a clarification. In this case, the function keeps going down to negative infinity in both directions. So it may be tempting to say absolute minimum is negative infinity, but in that case, we'll say that the absolute minimum doesn't exist. We're going to restrict ourselves to just numbers. So I'll just say that here. Here, there is no absolute minimum. So to further clarify what we mean, there's also no local minimum because there's no bottom of a bound. Any questions about that? And similarly with maximum, if it goes off to positive infinity, we'll say it has no absolute maximum. Now that will show up somewhere. But this these definitions are all contained under the topic extreme value theorem. What does the extreme value theorem say? Well, do I want to do that or do I want to build to it a little more? Before getting there, no, let's state it and then get there. Extreme value theorem, a statement. A function, how do I want to start this sentence? If f of x is continuous on the closed interval a to b, then what? Then f attains an absolute maximum and an absolute minimum. Somewhere on that interval. So all we need is a function to be continuous on a closed interval a to b, and the function will, or then the function will hit a largest value and it will hit a smallest value. Now, what could that look like? Well, it could look like, well, a few things, but the next two graphs will show can be used to figure out all of the different cases that this could look like. Observe. We're going to take two graphs. Let's make it look like this. Let's call A that value. Let's call B that value. And let's mark off A to B on the function. And let's do one like this. Let's call this g of x. Let's call this one A. Let's call this one B. Let's shade it in. So we have here two functions. We have two closed intervals. We have two setups for the extreme value theorem. The extreme value theorem says, given a continuous function, which we have in both cases, the function will hit a maximum and it will hit a minimum. And the question is, where do these values occur? So here, where is the maximum? Well, the maximum on A to B is that y value at B. So here, the absolute maximum, let's abbreviate that, ABS max, occurs at an endpoint. Where does the absolute minimum occur? It's the lowest point there on A to B. And the absolute minimum occurs at a point. It's at the bottom of a mound. What happens at the bottom of a mound? Well, we can interpret that using the derivative. At the bottom, the tangent line is horizontal, so the derivative is 0. In the second case, the maximum occurs also at, the minimum occurs at an endpoint, the maximum occurs at the top, which is where the derivative is undefined. And the extreme value theorem says that's what you have to look at. So we'll do that next week because the church bells just rang. So yeah, I wasn't positive going into this week that we'd actually go through the examples. So again, number 4 on the homework, you can skip over. Although you actually can use this observation to answer 4 that you get the maximum. I forget where. I think it's at 2. And the minimum's at 5. But you don't have to do number 4 for this week again. And we'll start next Wednesday with this statement, and we'll do a couple examples. Any questions? Anybody have questions about anything we've done? So for this weekend, it's definitely a good idea to practice some of the chain rule questions. Now, it's very important, especially if you're going to take Calc 2. But you do have homework. Let me know if you have any questions on 1 through 3. Other than that, I hope you have a good weekend, and office hour will start right now.